Hello, so today we are going to do this problem, which is part of Leetcode daily challenge. Find maximum number of marked indices, okay? So the problem says we get a zero indexed integer array of numbers, and initially all of the indices are unmarked, and we are allowed to make this specific operation any number of times. The operation is to pick two different indices that are unmarked, I and j, such that 2 multiplied by number at I is smaller or equal to the number at j. And then we mark those two indices, which basically means we can't take them again, right? And the goal of the problem is to return the maximum possible number of marked indices in the array using this operation, any number we want. So we want the maximum number of indices we can take using any number of operations. Okay, so for example here, what we can do is first pick the index 2 and 1, so 0, 1, 2, and 1. So that's 5. So because 2 multiplied by 2 is 4, 4 is smaller than 5. So we pick those two indices. We mark them, so we can't take them anymore. So only 3 and 4 remaining. 3 multiplied by 2 is 6, so it's bigger than 4, so we can't take these. And so we can take only 2, right? So that's sort of the idea. The constraints are large-ish. We have 10 to the power of 5 numbers, so that tells you can do an oven squared algorithm. Okay, so how can we solve it? Okay, so how can we do this? So what we want is to form a pair such that 2 multiplied by number at I is smaller or equal to number of j, right? So we want to make a pair. We want to count the number of pairs and the total number, so it's going to be the number of pairs multiplied by 2, right? Now to make k pairs, to be able to make k pairs, right, it's always better for us to try the smallest possible number, because if you pick a bigger number, right, then there is less a chance to find something that is bigger than it, right? Let's say you have 2 and 3. Which one give you a better chance to find a number later on bigger than that number? Well, the smallest number is always better to pick first, because then you would have 4. Otherwise, you would have 6 for 3 by 2. And so it's easier to find bigger than 4 than bigger than 6, right? If you find something bigger than 6, then that would be bigger than 4. But not necessarily everything bigger than 4 is bigger than 6. For example, 5 is bigger than 4, but not bigger than 6, right? So if you later on you have 5 and you had picked 3, you won't find a solution. And this is exactly what we have in the first example, right? And so that's the first observation. And so this tells us that we should sort the array immediately, right? So this tells us that the other thing that sort of hints that we can sort the array is that the problem says it doesn't matter, the order of indices doesn't matter really, you can pick any I and j, right? So that means we don't have to maintain the array in the same order, and so we can sort it. Okay, so the first observation is to sort the array. Now we said we have to, if we make 2 k pairs, right, that means we need 2 k elements in the array, right? So the number of elements in the array is n, so this number has to be smaller or equal to n, right? So that tells you the number of pairs has to be, right, which is k, has to be smaller or equal to n divided by 2. So we can only make at most n divided by 2 pairs, right? So that's another observation. So sort the array and we can make up to n to divide by 2 pairs. And so this is exactly what we can start finding. The intuition is that we first know that the first element, right, as we said here, needs to start at the smallest value. So once we sort and we have, let's say, array for, let's say maybe the first example, once we have an array like 2, 3, 4, 5, right, we want to start the first element of the pair, which is I. It's always better to start it at the first index, right? Because we want to pick the smallest value. That's what we said earlier, is we want the smallest value maximizes the chance of finding a valid j, right? And so now the question becomes, because we are trying to find 2 pairs, so we can try to use 2 pointers. The question becomes, where do you start your second pointer j? Okay, and so what I'm proposing here is we will start it at the n plus 1 divided by 2. So sort of at the middle, so sort of here. And if you have like an odd length, let's say 4, 5, 6, then I'm proposing to start it here, right? Now, why is that the case? So for example, with this array 1, 2, 3, 4, we're proposing start j here and start j here, because we need at most n divided 2 pairs, right? So if you start your j here, you won't find n divided by 2 pairs, right? Because you have only one element for I, right? And so to be able to maximize the number of pairs, right, you need I to be only the first half, so that you can have a possibility of having a second half to pair it with, right? And so that's where the idea comes from. And so this is basically the calculation. If we use n divided by 2, n plus 1 divided by 2, then for this array, we would be here. For this array, we would be here, right? And you may say, why push it here and not put it here for the odd elements? Well, if you put it here, then you are guaranteed to have only 2 elements, 2 pairs. But if you put it here, also you are guaranteed to have at most 2 pairs, right? And here we are guaranteed to have 2 pairs. But putting the j here doesn't maximize your chance of finding bigger elements. And so, but putting it here maximizes your chance, and anyway, you only get to have 2 pairs at most, right? And so may as well put it in the place where you would have the highest chance of finding a valid pair, right? The other thing is that also, just to prove this j thing here, let's take a counter example. So the second example we have in the problem is 9, 2, 5, 4. So once we sort it, we get 2, 4, 5, 9. And so let's say we don't put j in n plus 1 divided by 2 here. Let's say we put it before. Right? We already know I has to be here for because we want the smallest element. But let's say we put j here. Then if we take 2 by 2, right? That's equal to 4. So we pair 0 and 1 because our j is here, and we advance our j here. And our I also needs to go, I needs to go here, so our j here. So we try to pair 5 and 9. But 5 multiplied by 2 is 8. Is 10, sorry, and 10 is bigger than 9, so we won't find another pair, right? Basically, if we do 2, 4, 5, 9, and we put our j here, we'll end up pairing these two, and then the remaining ones can't be paired. But that's not the best solution. The best solution is to actually pair 2 and 4, 2 and 5, and 4 and 9, because 2 multiplied by 2 is smaller than 5, and 4 multiplied by 2 is smaller than 9. So this is actually the better pairing, is to place j in this position. So this is the counter example, but just also by just proof here is that you need to maximize, you can have at most 2 pairs here, right? And so to maximize your chance of finding the 2 pairs, you need to pick the largest one. If you put it here, there is a higher chance if you have 4 than if you have 3. So that's the idea. Okay, so so basically, just to summarize, when we start with the smallest element I, smallest number I, we want the smallest j that will work, right? And so the smallest j that will work is and maximize our chance of finding the maximum number of pairs is the middle here. Okay, I hope that the proof sort of makes sense for you. Now, how do we implement this? Let's show it on an example. So let's take, for example, take the first example here that we have, which is 3, 5, 2, 4. So first we sort, we end up with 2, 3, 4, 5, and let's put our indices. So our indices are going to be 0, 1, 2, 3. So our j is going to be here, our I is going to be here, right? And so each time we try to pair I with j. If we can't, we move j, because if we move, we will get a bigger number and have a higher chance of finding a valid pair. And so we say 2 multiplied by 2 is smaller or equal to 4, so we are good. So the count of pair we have, we need to increment it, right? So let's increment that. So our count is now 2 because we have a pair. And so we move I and we move j, and so 3 multiplied by 2, that's unfortunately 6, is bigger than 5, so we return count, and this is the best we can do. Now let's run it on the second example, which is 2, 4, 5, 9. So again here, I start here and j start here. 2 multiplied by 2 smaller than 5, right? Because it's 4. So our count here is going to be equal to 2. We advance our I, and j, since it's marked, we go here. Now we have 4 multiplied by 2, which is 8, it's smaller than 9. So our count is 4, and this is the answer. Okay. Now let's take a little bit, maybe 4, 5, 6, 7, 9, right? So here 0, 1, 2, 3, 4, 5. And so our count is 0 initially. And so we put I here, we put j in this position, right? And so 2 multiplied by 2 is smaller than 6. So our count becomes 2. And then we move our I pointer here and j pointer here. And then we check 4 multiplied by 2, is it smaller than 7? No. And so we move our j. Is it smaller than 9? Yes. So now we have 4. And now if we move I, we are done because j reached n. Okay? And so this would be the answer. Now, how are we implementing this? Well, we can just keep it. We can either iterate on the i's or iterate on the j's, right? And the easiest solution is actually just to iterate on the j's. What do I mean by that? So basically, you place j here, and you move I only if you find that a j that is bigger than it, right? So you start with j here. So it's going to be from n plus 1 divided by 2 all the way to n, right? And then only if the number in j is bigger or equal, right, to 2 multiplied by the number at I starts out as 0. Only if that's the case that we move I, right? So here we find that 2 multiplied by 2 is smaller than 6. So we move I because we found the solution, and j moves just with this slope. And then we find that 4 multiplied by 2 is not smaller than 7. Right, so we don't move I, we keep I here, but we move j. And when we move j, we find the answer, and we are done because this slope is done, right? And so, of course, here, because we find a valid pair, we need to increment our count by 2. So that's the idea. You could also choose to move I, and then inside choose the loop to be by I, but inside the loop, you would need to move j. You could do it whichever way you want. Yeah, so let's implement this version and make sure it passes test cases. Okay, so let's implement the solution we saw in the overview. So first we said we need to sort the array. And we need our count, which is equal to 0. And then we need I, which is going to be equal to 0. And we also just need n. And so now our j, we are going to just start from, we said j needs to start from n plus 1 divided by 2. Because this works for both even and odd length, right? And we go all the way to n. So basically, we iterate j on the right half of the array. And now, if this j is actually a valid pair with the current I, then we found a pair, and so we need to move I. So we need to move I, and we need to count this pair. So basically, means basically that ij is a valid pair. We actually don't need to maintain a marked Boolean array or anything like that, because when we find a valid pair, we just move our pointers. We want to go back to these pointers anymore, right? So here we need to add 2 because it's a pair. And then at the end, we return count. And that should be it. So pretty straightforward once we have the logic. Let's run it and let's submit. This passes our test cases. Now, in terms of time complexity, this is O of n, right? This loop here is O of n. And then we are not using an extra variable. Except here, we are, in terms of time complexity, we are doing a sort. So this is O of n log n. And this is O of n. But this is the highest term. So overall, we can say we have O of n log n time. And in terms of space, we are not using any. So O of 1 space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.